Continuing on with my motor drive design, I have decided to restructure the analog output a bit. So my original idea was to try something completely new. I wanted to have potentiometer emulation. So I wanted to be able to sort of connect these outputs just as though they were potentiometers, so that the other side would be able to feed a voltage into this input here, and then the voltage would be divided by the internal potentiometer inside this digital potentiometer chip, and this input would be connected to ground, and in the middle I would get the signal output. The problem that arose in this design is that driving this chip from 5 volts essentially requires the I2C interface to be 5 volts as well. And also there is a limit to the input here. It is pretty much limited to to the supply voltage. So if I make the supply voltage 3.3 volts, then the maximum input here is specified in the datasheet as 3.3 volts. So I'm not really sure what is true and what isn't regarding the behavior of this chip when it comes to feeding voltage into the resistor that's inside here. So I decided that I'll go with a more sort of more conventional analog output. I will use this chip to control the input to an amplifier, which is going to be the same opamps that I use here. This is a rail-to-rail input and rail-to-rail output amplifier. So the output here will be so I will drive this chip from 3.3 volts, and I'll set the gain of the amplifier such that the output will swing between slightly over ground level to slightly below 5 volts. So this will be an analog kind of analog joystick output, which is very useful if this would be connected to some other control board that expects an analog input. So instead of this being a resistive connection, this would be now instead a true analog signal. And for this version of the board, I will go with 5 volts. I have an idea of perhaps allowing the user, allowing this to be configurable so that it can run either from 0 to 5 volts or from 0 to 12 volts. But I think for now I'll just use 5 volts because I have an actual use case for 5 volts while I don't have a use case for 12 volts. So it is rather much more useful to just keep this circuit as simple as possible and use 5 volt outputs. So I will just copy the amplifiers here. Let me move this circuit a little bit higher up. Let's see. And I'll just remove the graphic lines so that we have a clean work area. And the protection diodes can be removed as well. So the idea here was to clamp the voltage to plus minus 5 volts. But we don't need this anymore because we're not going to be feeding any current into these inputs. This will be a pure output. And actually the connectors will go as well. So pretty much everything goes here. let's see. So let's also delete that. Okay. I'll copy this. I'll copy the units one by one. It's going to be, these are actually different units in the same chip, so it's A, B, C, and D. I will feed the units. Let's see, let's put the units perhaps here. So this will be VDD 3V3 instead of 5 volts. And I'll also connect VDD 3V3 to the potentiometer, across the potentiometer. So this is 10K potentiometers. I could actually even use a larger potentiometer. Let's see. Divided by 10,000. 330 microamps is going to be constantly drawn here. Okay. And this will connect to 5 volts. Let's be absolutely perfectionist about this. I'm gonna move this on the square. So the negative one will connect, let's see, put the ground reference there. So the negative will connect using negative feedback. So it will be a resistor to ground and a resistor from the output. And the resistors are calculated. Let's bring up the calculator. So I've already calculated the resistors. It's going to be a 10K and 5K. So let's see here. It's going to be. So have a resistor here. There's a good YouTube video called opamp gain. It kind of explains the concept. So I'll put a resistor of 10K from the let's see, from the negative terminal to the ground, and then oh crap. Okay. And then let me just put a 5K resistor here as well. So 5K. The 5K resistor is going to be the feedback resistor. So it will feed the op-amp. Let's see. It will go from the output and to the ground here. We can even do like this. We can move this over here. And we can connect the ground through it. Is this correct though? What the fuck am I doing? What the hell am I doing? I'm doing something really stupid here, okay? This has to go directly to the so this has to be a voltage divider, so obviously it's going to be like this. This will be a voltage divider which connects the output to the input, and this will be connected to ground. So and this will be this will connect directly to the this will go to the potentiometer. So and then there will be a second stage and a third stage and a fourth unit. So 4 units. Except I'm gonna just do like this. So let me see here. I have to use copies of specific units, but I can copy this one and just duplicate it so that I can more easily let me see here. So I should actually copy it and then I should paste. This is better. And paste. And paste. Okay. Alright, maybe I should put it like this. Let's see. I'll just bring it in like this. I have to remember to delete these ones and move in the copied ones that have the correct designator. And then maybe I can put these ones here. Although I'll just move it a little bit more out to the side because I want to fit a connector here. So this should ideally be like some kind of analog connector that that has proper shielding and stuff. But for this, since this is a bit of an evaluation of this circuit, and it's not going to be transmitted for long distances, I think I'll just go with the same screw terminal that I had for the button inputs and all the other connectors. switch. Let's duplicate this and just make this an analog output. Okay. Okay, I'm gonna add this and this. Let's see. Wait a minute, so the A has to be G and D. No, the A has to be the power supply voltage, while the B is G and D. I'm going to connect this one here. And I should move this a little bit. Alright, so the way this circuit is going to work is that the potentiometers will set the voltage on the input of the amplifier, and the amplifier will increase this by 1.5 gain, so the output will, in fact, this is wrong, so this would be 5 volts. So the output will swing between ground and 5 volts in this case. And all of our I2C communication will be done using 3.5 volts, 3.3 volts. Okay. going to be exciting to see how all this works. I'm going to review this schematic as well. This is not the final. So put it there. Okay. So I got the analog outputs there, and I need to also create a similar schematic for this. So this will be the control for the overcurrent limit. Let's put a test point there as well. I'm going to put test points on each one of the inputs, and also on, or actually I don't need anything on the output, so just the input. Okay. And it would probably be nice to have test points on these ones as well. So the stuff that goes into the multiplexer. And we can also place a test point on the output of the multiplexer. Great. So, solving this issue with the overcurrent limit. I'm going to use an opamp for that, the same opamp that I used here. I'm going to copy 2 units here. Let's see. I think this will be A and B. Yeah, A and B. And the way that this is going to work is that this will be connected to VDD3.3. I've created another VDD rail called VDD3.3 MCU, but I've had a few considerations to maybe just merge them together. The idea being that certain things can be powered off separately, but that's kind of undecided yet, how that's going to work. I don't want to add too much stuff that is like good to have, because that's just a good way to increase the BOM cost without increasing the value. I want to have enough, I want to provide means to do stuff. So like, for example, with the analog inputs, I provide means to control an analog, or I mean analog outputs, to control an analog driver card, which can drive some other servo using an analog signal. So it's kind of like the Unix philosophy, provide means, not policy. So we provide means, but we do not impose a policy as much as possible. Let's place this precisely in the middle, or maybe actually a little bit farther down like that. Now, because this one will have to move. I think this can actually be unity gain. Or wait, does this need any voltage translation? I don't think so. In which case we don't even need the amplifier here. In which case we can just basically, yeah, there's an A0 there, so that will have to go to VDD 3v3 if this is going to connect to the same I2C bus. And actually, I think it's as simple as just making it connect to let's ground all the resistors here. I'll ground the B terminal on all resistors. It doesn't really matter. And then this will be connected to 3.3 volts. And I need to check the DRV8302. And I need to check the level on this MOC. So input pins. High input. It's 100 kilo ohms. Oh wait, so this MOC is actually the overcurrent mode. It is OC adjustment that we need to connect to the resistor output here. So let's see, we have OC adjust. Okay, so the voltage will be used to preset the trip value, and the trip value OC has to meet following equations. DVDD is 3.3 volts, so okay. Right, there needs to be also resistors that connect this just in case that this chip does not work for whatever reason, like maybe I happen to connect the I2C ports in the wrong way, then it's very important that this can be bypassed. I'm going to delete this. So this needs to be bypassed to VDD 3v3. That will be our current adjustment 1 and our current adjustment 2. Okay, now Okay, it has to be more than 1 kilo ohm, which it is now, because the digital potentiometer is 10K. Okay, right. So dV/d is 3.3 volts. Let's see what this means. So we have, let's say we have R1 at the top and R2 at the bottom, and that we are kind of keeping the potentiometer at the higher level. So R1 will be 1K divided by 10K, because the sum is always 10 times 3.3, and then that divided by 0.0075. So that will be 44 amps. Let's make it like this. So that was actually yeah, that didn't matter, of course. But this seems to be, so R2 is at the bottom. So if R1, oh, okay, so it's R2, sorry. So of course, so if R2 is 9.9, which means it's at the top, oh, we get like 400 amps. Come on. So then R1 is almost at the top. Let's see what if we put it to 9. So probably like 1K. So this would be if R1 if R2 is 1K. So if this one is 1K and this one is 9K, then our limit is at 44 amps, which is kind of high, considering that we only have 256 levels to choose from. So what if I instead set this to 5? I was thinking if I fix R1 to 10K and then use the potentiometer's R2, that would get a little bit better range. But it seems like it should probably be wait, let's see. So if that one is 5, and then divided by 15, what if we have, if R2 is 5 and the other one is 100K, so that would be 105. And what if we make R2 1K, and we're limited at 4 amps. And let's see, so what if R2 is 10K? Then we have 40 amps. So it looks like probably a good idea is to place a resistor. So instead of placing these resistors, what I'll do is place 100K resistors, and I'll just remove this connection so that I only have a connection to ground, and these resistors will be 100K. and they can obviously be replaced with 0 ohm resistors if this functionality is not required. So let's search for resistors. What do I have? I have 135k. I want to use some resistor that I already use somewhere, preferably some resistor that I use a lot. So what could be a resistor? I guess I could take 135k. Although that would actually limit the, so if I make that one 10k and 145, so that would be 30 amps. And the lowest one would be, so if we take, let's see, if we take 10 and divide that by 256, 0.04, so 140. This is actually not entirely correct, but it just gives sort of a feel for the precision level here. Okay, that seems okay. That seems fine. Should I go with this? Let's see, res 147. Res 2 is 24k. No. 4. 53k. I think I used the 100k though, so I'm gonna check this. 100k, do I use 100k? Probably not. So since there's also something else that I could do to make things a little bit more flexible. I can connect the OC adjustment pins to GPIO pins, so that I can, if required, just pull them high. So if these pins are pulled high, then the overcurrent threshold will be much, will be basically the maximum. So these ones will be no connect. And all current adjustment will be there, so I'll connect them to some GPIOs. Possibly actually something that, actually let's connect them to ADC pins. Yes, we can connect them directly to ADC pins, just so that we can sense the level at which the potentiometer currently is in. This is actually very useful. ADC in 7, in 8, SPI 5 MOSI. least this one can go there, but I'm not sure about this one. Maybe I'll leave it there for now. So this pin is always at 3.3 volts or at 0. Now there is something else that I need to do, and that is adding opamps to the voltage sensing here, because I'm using such high resistances here that any sensing that's done by the ADC on these pins is going to be completely off. And that is because there is a minimum current requirement in order to charge the ADC sample and hold capacitor. And if this current is way too low, which it's going to be in this case, where the voltage goes through a 135k resistor, then it takes longer time to charge the capacitor, and the readings are going to be wrong. And this is an important thing to consider. I'll put some text there. I'm not going to add it right now, because I want to take a break. But I could connect this SCL and let's copy this. Yeah, this one is only available here, so okay. So there was an I2C bus that I used here somewhere, so what was that? Was it for the, was it here? APSCL. Where did I connect APSCL? There we go. So I'm going to connect the other chip to this connection as well. What is this? Okay. So move, rotate, and then move this and rotate this. And then this one. So these ones will be connected to the same I2C bus, and I'll connect the reset pins a bit later, after I've added a few more interfaces. So I'm gonna also add a connector for the LCD. Just so I don't forget it. there will be an LCD connector on this board, allowing connection of a simpler LCD display, which is usable, very useful when there are also buttons connected, and it will allow viewing the status and the details of the operation of the drive. So this is not just a drive control board. It's actually a control board that can be connected to joysticks and buttons and other types of user interface devices. So this is going to be very useful. I'll leave it here for now. I think the next step would be actually adding the opamps to the sensing circuits. I'm going to leave that for the next video, and I'm going to stop this video right now. So thank you for watching, and I'll see you later. Bye.